In the previous video, I was talking about self-modifying code. Let's be honest, that's kind of a hack. That's not something you would use in real life. In this video, I will talk about dynamic loading, which is a very important tool in your toolbox if you write C or C++ code. So what is that? This API is a C API. It has some consequences for C++. It's a bunch of functions. One of them is dlopen. Dlopen. So how does it look like? You support it is similar that you extend your code at runtime without closing your process, without exiting your process. And the way to do that is that you ship the extra code via a shared library. And shared library, this is a C API. The shared library has a bunch of maybe global variables, a bunch of functions. The functions are the key point. Then the dlopen is the first entry, which expects a file name. A file name is the shared library, and that will map that library to the virtual address of virtual memory of your process. Then the next function called dlsym will locate symbols in that newly opened code. Let's take a look at it. Let's take a look at an example, so it is much more simple to understand there. I have a very simple main function here. This is I rewrote an example from the man page. So let's go over it, what this does. So I will expect a doIt function from the shared library. I go into a loop, and then I will wait for an input from the user. And after that, I will try to open a local file, doit.so. If I do some error checking, then next I will try to locate a symbol called doit. Then I will cast it to the correct signature, and then I will call it. Then I will unload the shared library from my virtual memory, and then go back to the loop. So it keeps opening up these SO files and keeps trying to call a doit function from it. Let's compile this now. So the only interesting thing here is that I link to the dynamic linker, the shared library. That's what implements the dlopen and the other functions. Let's call it now. And now it waits for an input. I press enter, and it prints out what error the dlopen got. So it can't open the file because it doesn't exist. I will leave this process open and go to a different window. So this way I wanted to show that we can load up some code that was not even written yet. Let's create now a doit function, and we will compile this into its own shared library. So the doit function will just print out hello. We will name it as the other process expects, so it will be named doit.so. And then we have to compile it in a position independent way, make it a shared library. So now we have the doit.so shared library. Let's go back to the other window. Let's press enter. And it printed out hello. And if we keep pressing enter, it does the same thing. So it opens that shared library, locates the doit function from it, calls it, then unloads the shared library. Let's leave it open, and let's create another version of it. Let's call it exit. So we will override the doit.so with this new one. Let's go back to the main function. Let's press enter again, and it exited. and we can see that the return value was 0, so exit success. Okay, so what's happening? Can we understand it a bit deeper? Yeah, sure we can. So let's do some experiment first, and then I will open the documentation. So let's take a look at first the shared libraries, what this main binary uses. So it has four shared libraries. For example, the libc and the libdl that we requested. Let's take a look at it with strace first. So it is waiting in this read call, so it expects our input. Let's take a look at above first a bit. So we can see a bunch of shared libraries, and I want to look at how they are being loaded at startup. So these are not the dlopen ones, but we will see a similarity. So we call an open, and this is the returned file descriptor. This will be always 3, as we see. So we can follow with this file descriptor what kind of other system calls we make. So here we see that it reads up the elf header of it and then probably interprets it. That is not shown in this code because that's not a system call. Then we see a bunch of mmaps, especially these ones. So how to interpret this? This is a virtual address that we would like to be mmapped. So that should be the target address. As this is at the startup code, these are surely free. So here is the return address what we get from mmap, and this is what we requested. These two does not have to be the same. So if I call it and just make up an address here, and if it's not free, then we will get a different address back here. But this was compiled in a way that surely there is room for them. Then what other? So this is the file descriptor. That's why we know that it is opened. That is referring to that file that we opened. So the libdlso. This is the file offset in that file, and this is how big of a chunk we take from that file to be mmapped to our virtual memory. And we can see what kind of. So this is an executable part, and the other sections. So it's very similar for the libc. It also got the third file descriptor because we closed the previous one, and we also see at the end a few mmaps for this. Now let's press enter now. So we opened. This was the exit shared library, and we see similar things. We opened that so. It got the file. It got the file descriptor 3. Then we read the elf header and then interpret it. I will show it in a document what it does. Then we make a bunch of mmaps. So this is the executable one. So starting at here, this is where in the file, in the shared library file, the exit function, the doit function that calls exit is located. Then yeah. So I think let's jump quickly to the documentation if you want to deeply understand how this whole process works. I opened 2 documents. One of them is the System.v application binary interface. This is a general ABI document which applies to all kinds of processors. You can, based on the titles, on the contents, you can guess what it is about. And then there is a processor supplement version. In my case, it's AMD 64, where you can read the nasty details for this instruction set. And here it has a section about dynamic linking, and this is the one that you should read if you are interested in the nasty details, apart from just moving stuff and mapping stuff to the virtual address. So one thing there is that it's that we need a position independent code. So if it would be not position independent code, then You can imagine that, for example, you have a jump instruction with an actual virtual address there, and that virtual address will be not correct if you map that code somewhere else. So what you would have to do then is that you actually have to patch all the instructions that has some kind of address, and then patch those addresses to point correctly. Now, this is actually doable, but it's not the nicest thing to do. So position-independent code uses relative addressing to get rid of this problem. Now, the one thing the thing that anything deeper than this, I will not talk about it, like the global offset table or the procedure linkage table, and what happens when you, so this is the 8 simple steps what happens when you locate first time a symbol. You can read up the details if you are interested. I will give a link to these documents below the video. Let's talk about use cases. Where is it? Where is this useful? Think about plugins. Well, for that we need a good example. Imagine, for example, a video player application that supports a few kinds of container formats and video types, and you have a client on your machine, and then you when you try to open a new kinds of format that the local client does not speak that language, then one thing it can do is that, for example, securely talk back home to a server and looks up whether there is a new shared library that supports this type of container. So imagine that you have a C interface playing videos and opening containers and finding things there. So, for example, play, seek, stop, and other bunch of functions. And then you have a bunch of shared libraries. They each expose their functionality through this interface, and then you can open them up with dlopen. So you talk back home for a new format that the local client didn't know, and then someone implemented it. Maybe your client is too old and did not have it locally. Then you can just download the code directly. Of course, this has to be secure, so you have to check whether this is really a valid code. And then you can load it up and then just start playing the video. You don't have to talk to the user that, oh, please install the newer version, or please restart your video to install this plugin, or whatever. No, your process can do this in the background with dlopen. So that's one use case. Another use case is think about game engines. Where the engine is written in C++ and you have an editor. So the game and the engine is both written in the same language. And imagine an editor where you can iterate over your game code, and you can see it next to it. So you change a few things in the code, changing some player logic or whatever, and then when you save that file inside the editor, then in the background it gets compiled, then it gets opened up. They change the previous version of that code at runtime, and then you can start looking at the new version of your game inside that editor. So one way to achieve this is with just dlopen. So I think the possibilities are endless. I think the nice way to think about them is really plugins. I think Apache uses these plugins as well. Another use case is that maybe you support so many things, and that actually only a user would use only 5% of those functionalities, but you have it locally, everything. So if you would load up all the functionalities at once, maybe it would take a lot of memory, and it would take long time, and you have a bigger attack surface. More code means more attack surface. So you can just dynamically loading up only the necessary plugins that you need, necessary functionalities. In some way, this is how the Linux kernel works as well with modules. Why would you pay the price of supporting some hardware that is an edge case and no one really uses it? But you can dynamically load up a module for that. Okay. Before I move on to C++, because I want to show a C++ code for this, maybe let's quickly go over other languages. So there is of course the dynamic languages with interpreted dynamic languages like JS or JavaScript or Python. So one of the common things there is that they have usually something called eval function that expects a string of code, and then it can interpret that code. Of course, the biggest problem is that this can be equal to evil in the sense that your colleagues will never approve a PR where you use that, because this is considered a security problem, and that they are right. But still, this is a very powerful feature. That's what you would expect from a dynamic language. You have a big runtime. Okay, what about Rust? I did not use dlopen in Rust, but I made a quick query for that. So let me show what I found. So this is a crate where we can see an example. So apparently someone just prepped up dlopen to be usable in Rust as well, which is not a big surprise, but I'm pretty sure that in the details there are some hoops that you have to jump. I did not use this one, so I can't really say anything about that, but it looks possible. Okay, what about for example Java? Now I did a lot of Java and C++ interface, so I can talk a lot about that. Java actually has a pretty nice story for this. So there is the Java class loader, where you can find classes and dynamically load them. So that's for Java code. But it also has something called System.loadLibrary, where you can call shared libraries written in C or C++, and you can load them up in Java. It also enables talking. You can create functions in Java called with a native prefix, which are implemented in C++ or C. You can also talk back from C++ code to Java through the Java native interface. There is a big documentation about that, what kind of things you can do. You can synchronize with the Java VM and attach things to that. So it has a pretty complex story about it. One thing it doesn't have is for example, it doesn't have System.unload.library. That's a quirk. Okay. Did I miss anything I want to talk about? Yeah, probably, but let's move on. So let me show a real-world C++ example, and let's talk a bit about C++. And so a real-world example I did like around 10 years ago. Okay, I have some code here. I copied. Oh, that's not what I wanted. Okay, before we get into this, I have to tell some story. Let's open this up, and then I tell the story to understand this code. I worked around 10 years ago. I worked at a startup where the product was live streaming application. Live streaming, think about YouTube just only for live videos. So the applications were mostly mobile phones. The mobile phones were the cameras, and they were the devices how you could record live. And this was after the iPhone came out, but before the first Android phone came out. and I was working on the Android application first. So what was the stack? Obviously, the UI was written in Java because you had no other choice. Then we also had a networking layer and a streaming layer written in C. It had responsibilities to talk to the backend, so we did not have to write it. We share this code between the iPhone and the Android and the other applications where you could write native code. So the backend communication was handled by that shared layer. Also, things like synchronizing the audio frames with the camera frames, and other bunch of business logic stuff that was completely shared. So that was in C, and then I used C++ to work on the streaming part that was Android specific. This was about getting the camera and the audio frames and similar stuff. Oh, we also had ARM assembly, which encoded the camera frames to it compressed it. Okay, what was the problem? The problem was that in the first Android, it had a version called 1.5 and also a name called Cupcake. That the Java camera API was absolutely broken. It copied the camera frames constantly and then dropped them, so the GC was running constantly. The best FPS we could achieve was 2 with the native API. So what I did is that Android was open source, so I went to the source code and looked at how the native camera interface looked like. And we figured out that we can compile code inside the source code as well. So we used the native camera API, which was a C-like API. It had a C-like callback where you got the new frames, and plugged that in to our chain. So this was a C++ code. We talked to our Java layer, and then we encoded it with ARM assembly and sent it to the C layer that synchronized the frames. And with this, we achieved 15 FPS. So this was a big success. So when the first phone came out, T-Mobile G1, then we had a working version, and that was a really slow phone. But the problem with Android was that they iterated very, very fast in the beginning. So like every 3 to 6 months, there was a new Android version. And when the next one came out, which was 1.6 called Donut, then they changed the private camera API that we were relying on. So our application was broken. Of course, this was not unexpected, but we had to keep up with this. So what changed? The earlier C API was replaced by a C++ class, basically. And we very quickly wrote, in just a few hours, we were able to write a new version that worked on Donut, but didn't work on Cupcake. In fact, you could not compile a Cupcake version on the Donut source code. So either this one or either that one. So the solution I came up with is that I created a shared interface which looks something like that, but I just made these up. Of course, it had a little more functions, but not a lot, with some usual camera functions that make sense. And then I implemented them in both Cupcake and in Donut. Here you of course you just see some dummy implementations for them. So after I did that, then the last step that was the most important one was that I separated it to the existing code to 3 places. There was the main code base that got the version number from the Java layer, are we in Donut, are we in Cupcake, and then it branched off from there. Then we created a version of the Cupcake camera that only had the camera functions in it and the Donut camera each compiled in a different source tree. One of them is in the cupcake source, the other one is the donut source. The main code was compiled probably always in the latest one, but it doesn't really matter. And then at runtime, the main function code, which did not have any camera function, it interacted only the interface, so we were able to compile it anywhere, made a decision and dlopened, made a decision based on the version and dlopened the right camera shared library. So we had 3 shared libraries. And this worked pretty well. We had a single application that worked both Android 1.5 and 1.6. Just to close up the story is that there was 2.0, 2.1, 2.2. 2.2 was the first version where the native Java camera API was not broken. It was actually usable and the GC did not kick in. And there we used the native API. On 2.1, we used actually the 2.2 API was already there. It was just hidden in Java. So in 2.1, I used reflection to call the 2.2 APIs in Java. 2.0, that's an entirely different story, but that died out. This was a luck that died out pretty fast. That was just Motorola Droid, and they upgraded to 2.1 pretty fast. So in the end, we had this decider code that sometimes we call the cupcake native shared library, sometimes we call the donut shared library, sometimes we call the reflection, and sometimes we call the native Java API. And all of these were handled actually in the C++ code, and that called back to Java if it was needed. So we actually had in the C++ code, we had a Java camera. The Java camera called back to the native API, to the the Java API. Okay, sorry, this was a long story. So what you can do in C++, you can either create a C interface for your C++ code. That's a possibility, and that can be useful if you are writing a library anyway. That's not an unusual thing to do. Or you can create something like this interface I showed. So this is a C++ interface for your code, and then you can call it like this. So here this code implements what I was talking about. So we make a decision. So this main function expects one argument, which will be 1 or 2. If you send 1 to it, then it will open the cupcake shared library. If the argument will be 2, then it will open the donut. Then I don't know why this, maybe I pressed tab somewhere. I don't know why it is like that. Sorry about that. And then we call, obviously you need to locate some symbols that are C functions. So I will show them in a moment. So we locate 2 symbols, create camera and destroy camera, which basically just creates a cupcake camera or a donut camera in both cases. So we call that one, and then we can use it, we can talk to it through a C++ interface. So we call init start stop, then we call the destroy camera that we also located, and then we close it. It's really I don't know why does it look like this. Okay, the other stuff is just basic error checking and print usage. Yeah, I promised to show those 2 functions. So these needs external C, so otherwise the dlsym can't locate them. They need C linkage. So these 2 functions, I'm using the new operator. I want to say that using unique PTRs here is not that simple. Let's go back to the main function first. Again, so if you see here that we call create camera, and maybe we could store this in a unique PTR, but that's actually a bad code, because if you call dlclose anywhere here, and maybe unique PTR only after dlclose, then that will break the application, because that code is already unloaded. So you have to be a bit careful. So I call here destroy camera first and then dlclose. So if these two would be replaced, then we would have a problem. If you find a nice way how to use unique PTRs here, then just let me know. Okay, let's compile all of these together and let's see whether it works. So let's compile the main function first. Then we create the cupcake shared library. Then at last we create the donut shared library. Okay, we have all of them. Then if you just call the main, then it will print out the usage. And if you call one, then it went to the branch of cupcake. So it opened up the cupcake shared library and used that object. If you call 2, then it will call the donut library, donut camera. So this is how you can use this dlopen library in C++. I'm sure that there are other ways. So if you find good examples, just let me know. And I think I will stop here. I talked too much already. Thanks for listening. Bye-bye.